Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, I'm going to show you how to create your own system of equations, specifically linear equations. And this will just help you if you're practicing for exams or something like that, and you find that reaching into the textbook, there's just not enough systems. I'll show you how they create systems and how I create systems for exams. So how do you do that? Well, we'll have two different sets of how-tos here. One for a system with unique solutions and one for a system with an infinite number of solutions. So let's go ahead and with the unique solution, the first thing you're going to do is decide on a solution. And I'm going to actually do this, create one as we go through these steps. So let's suppose that we want a solution that looks like this. Let's make it somewhat ugly. Let's say the solution needs to be 1/3, comma, -2, comma, I don't know, 4. It's not terribly ugly, honestly, but it's got a fraction in there and most people shy away from that. And then you start creating equations using arbitrarily chosen coefficients on the variables. Because I have 3 unknowns, I need 3 equations. Let me just write row 1. You don't have to do the row 1, row 2, row 3 business, but I'm just showcasing where I'm placing my equations. And you don't need all variables present in each row. So you could skip variables. For example, my row 2, maybe I want X's and Z's. And maybe my row 3, I want Y's and Z's. Let's just pretend. You're going to throw some coefficients on there. Now, I say arbitrarily chosen coefficients on the variables, but if you want to make your life a little bit easier, if you have a solution that involves a fraction, choose coefficients on the related variable, x, that will kill off that fraction. So, for example, maybe a -9 here, because -9 times 1/3 would give me a nice, pretty integer. And same thing on the x in row 2, I'll put a 6 there, okay? And then the other ones, I'll just throw on some numbers. So let's go -1 and a +3. Let's do a -5 here. Let's do 2 and let's just do a plus. All right. Now what you're going to do, after you somewhat arbitrarily choose the coefficients, you substitute in the solution to determine the constant on the right side of each equation. So I'll go to this first equation and I'll substitute in 1/3. So I get -9 times 1/3. That'll give me -3. I will substitute in a -2 for y. So minus a -2 is a +2. And I'll substitute this 4 in for z. 4 times 3 is 12. And so the right hand side of this equation will be 14 minus 3, or 11. And then you do the same thing for your second equation. So 6 times 1/3 is 2. -5 times 4 is a -20. And so this is a -18. And finally, the last equation, 2 times a -2, that's a -4. And plus 4, that's going to be 0. So my system of equations here is going to be a -9x minus y plus 3z is equal to 11. 6x minus 5z is equal to a -18. And finally, 2y plus z is equal to 0. I'm guaranteed that system, as long as I've done my arithmetic correctly, I'm guaranteed that system has a solution 1/3, -2, and 4. Let's see, stop once you have as many equations as you have unknowns. We have 3 equations, 3 unknowns, we're done. Write the system with your arbitrarily chosen coefficients and constants determined from step 3, which is what we did, and then we can solve it. So this is just for practice. You can now go through and solve this. You could also like when I create systems, I move things around. So I would add y to both sides here, for example, or I might subtract 6x from both sides of that, right? So that I hand somebody a system and they still have to, at the very beginning, do a little bit of work. Oh, I have to get all variable terms to one side, so I'll subtract y from both sides here, and I'll add 6x to both sides here. So just to let you know, that's how those manipulations occur. You can also get really tricky and divide everything by numbers. For example, I could, if it were, let's say, a homework or an exam or something like that, I could start by dividing this first equation by, let's say -9. So I'd get x minus 1/9 y plus, oops, I'm dividing by -9, so it's a plus 1/9. Divide by -9 is -1/3 z and equals -11/9. So that could be the first equation, and it looks really terrible, but as long as you, as the person who is the recipient of this system, as long as you recognize, I need to multiply both sides of that first equation by 9 to get rid of those fractions, you will always end up back at this very nice system. So that's how systems are created. Very nice, easy idea. Let's go ahead and solve this system. Why not, right? And this time, because we have some equations that only involve a couple variables, I'll use substitution. Why not? So I'll take this row 3 here, and I'll solve it for z. Z is equal to a -2y. And then I'll go ahead and maybe plug that into a different equation. So let's see, this second equation here, I get that 6x is equal to 5z minus 18, which means that x is equal to 5/6 z minus 3. And once you get to here, you go ahead and let's see, actually it'd probably be easier to solve this top equation right here for y, and then you would plug all that stuff in the top equation. So let me do that. Y is equal to a -1/2 z. So now I have y written in terms of z, and I have x written in terms of z, so I can plug those into the top equation and find out what z is. I'm not a big fan of substitution for large systems, as you could probably tell, because it's a little bit messy, but you could totally do it this way. Essentially, you just pick a variable you want everything to solve for. So in this case, I didn't do it initially the right direction. I should have just said, let's solve everything for z. So this first, the third equation here, I solved for z. So y is equal to -1/2, or I write everything in terms of z. That's what I mean to say. So write everything in terms of z. So y is equal to -1/2 z. Then I go to that second equation, I say write x in terms of z. So you get down to here. And then I go to the top equation and I say, okay, great. Now that I have everything written in terms of z, I'll substitute that into the top equation. I have -9 times x, which is 5/6 z minus 3, minus y, which is a -1/2 z, and then plus 3z is equal to 11. It's not the best route. Honestly, I still would have used elimination here, but you could totally do this. So let's go ahead, and now that you have a single equation involving z's, let's clean it up. Distributing that -9 through each of these terms, you'll get a -9 times 5, which is -45, over 6z, plus 27, plus 1/2 z, plus 3z is equal to 11. And then let's see, 3 goes into both 6 and 45. So you have a -15/2 z's plus 1/2 z. That'll be a -14/2 z, which is a -7 z, plus 3z is a -4 z. And I'm going to go ahead and subtract 27 from both sides, which is a -16. And let's see, divide both sides by -4, and you get z is equal to 4. Once you have z, because you wrote x and y in terms of z, you'll be able to find x and y very quickly. For example, y is supposed to be negative 1/2 z. That'd be negative 1/2 of 4 or negative 2. So y is a negative 2. And then x is 5/6 z minus 3. Z is equal to 4. So this is going to be a negative 26 minus 3. 3 goes in, or 2 goes into 6 3 times, 2 goes into 20 10 times. And we have 10/3 minus 9/3, or in other words, 1/3. Now remember, what we wanted the solution to be was, let's make sure, 1/3, negative 2, and 4. Notice x is 1/3, y is negative 2, z is 4. So that's a way to create a system of equations and then to solve it. And again, I probably would not have done this system using substitution. I just decided to at the last second. All right, so that's kind of nice. You can now create an infinite number of systems of equations for you to practice on. But what if you want to create a system of linear equations with parameterized solutions? Well, that's a little bit more daunting. You can see with the number of paragraphs I have going on here, but it's not actually too bad. You just have to follow some steps here. Decide on a parameterized solution. The variable associated with the parameter will be called the dependent variable for this how-to, and the remaining variables will be called the independent variables. So that's just a language thing so that we can all speak the same language here. So let's go ahead and decide upon a solution. Let's say that I want my solution to be 1 minus 2z and let's let the y be negative 2z, and z will be z. That's a parameterized set of solutions, right? So we've decided that z will be our dependent variable, and the remaining variables will be called the independent variables. Technically speaking, actually, it should be the other way around, but whatever. I'm not that concerned about it. I'm just using it for this definition. Start creating equations using arbitrarily chosen coefficients on the independent variables. So on x and y, choose whatever coefficients you want, but we're not going to include a term for the dependent variable. So let's go ahead and just create a system of equations. I'll say 2x minus 5y and negative x plus y. And let's do one more here because you need 3 equations because there are 3 unknowns. Let's do, I don't care, negative 3x plus 7y. Okay, so we have something like that. And what we're going to do is create some equal signs here. All right, so let's see, start creating equations using arbitrarily chosen coefficients on the other variables. Do not include a term for the dependent variable, the z. Substitute in the solutions to determine the right-hand sides of each equation. Okay, so let's do that. Since I'm saying that x is equal to 1 minus 2z and y is equal to negative 2z, we'll substitute those in. So that's 2 times 1 minus 2z and a negative 5 times a negative 2z. So this will clean up a little bit. Let's go ahead and see how this cleans up. This will equal 2 minus 4z plus 10z, which is going to be 2 plus 6z. We'll do the same thing for the second equation. So a negative 1 minus 2z and plus a negative 2z. Now this is kind of a weird one, but that's okay. That's all right. We could do this. Plus a negative 2z. This one you actually do not get a z on the right hand side, but that's totally fine. You don't need one. So negative 1. And then the final one here, you have negative 3 times 1 minus 2z plus 7 times a negative 2z. And that'll come out to be a negative 3 plus 6z minus 14z. Double check my mathematics. Yep. And that'll be negative 3 minus 8z. All right. So far, all we've done is chosen a solution, pick some arbitrary coefficients for x and y, plugged in our solutions for x and y in and found out what the right-hand sides are. So note on step 3, the right-hand side should now contain a constant term and a term with a dependent variable. Stop once you have as many equations as you have unknowns. We have 3 equations, 3 unknowns. Write the system with your arbitrarily chosen coefficients and the expressions determined from step 3 as the right-hand sides, which I'm not going to bother doing. I'm just going to leave it like this. Whoops. I'm going to leave it how you could see it in these rows 1, 2, and 3. And then I'm going to add move the variable terms with z's to the left-hand side. For example, row 1 will be 2x minus 5y minus 6z is equal to 2. Row 2 will be a negative x plus y is equal to a negative 1. And row 3 will be a negative 3x plus 7y plus 8z is equal to a negative 3. You now have a 3 by 3 system of equations which has an infinite number of solutions, and you can parameterize this. So let's go ahead and parameterize this, or basically find the solution. So somebody comes in, they say, here's your system of equations for an exam or whatever it may be, a quiz, exam, whatever. And they say solve, and you say great. And they say, by the way, I want your answer written in terms of z's if there's an infinite number of solutions. Let's just pretend they say that. You say, okay, well then I won't get rid of z's. I'll use elimination and I'll get rid of the x's because that looks a little bit cleaner and easier to get rid of. So I'll take row 1 and I'll add it to row 2. If you do that, you'll get 2x plus a negative 2x, those disappear. You'll get a negative 5y plus 2y, which is a negative 3y. You'll get a negative 6z plus 0z. And that is equal to, you'll get 2 plus a negative 2, or 0. Okay, that's kind of clean. And then you look back and say, okay, how else can I kill off an x? Well, you could take the opposite, or negative 3 times row 2, negative 3 row 2, and add it to row 3. If you don't believe me, just do it. Negative 3 times row 2, you'll get a positive 3x plus a negative 3x gives you 0 x's, which is perfect. That's what we wanted. Negative 3 times y is a negative 3y plus 7y is 4y. Okay. Let's see. Negative 3 times 0 is 0 plus 8z is 8z. And finally, a negative 3 times negative 1 is a positive 3 plus a negative 3 is 0. You say, great, these equations look totally different, but they're not. But they look totally different. So let me group them up into a new system with just y's and z's. Negative 3y minus 6z is equal to 0, and 4y plus 8z is equal to 0. Now, a little bit of a hint for you. When you're solving a system of equations and you're deciding, okay, well, I'm going to use elimination, maybe I'll kill off y's or z's or something like that, you might want to look at dividing an equation by something that all terms are divisible by. For example, in that top equation, everything's divisible by a negative 3. In that bottom equation, everything's divisible by 4. So you might want to just kind of clean up your equations a little bit. If you divide the top row by negative 3, you get y plus 2z is equal to 0. If you divide the bottom row by 4, you'll get y plus 2z is equal to 0. You know that if you were to subtract these equations from each other, you would get 0 is equal to 0. And so this system should have an infinite number of solutions. Infinite solutions. And now that I know that, and I've read that they want me to answer with only, if I have an infinite number of solutions, they want me to parameterize in terms of z. I'm going to solve everything to be in terms of z. So in other words, y should equal negative 2z. Z itself is just z, so I don't have to really do very much there. So there's what z and y are. And to find out what x is, I'll go to any equation that involves x, really. So the second equation is actually pretty beautiful. That's a negative x plus y, but remember y is a negative 2z. and that is equal to a negative 1. Let me zoom in there. It's equal to a negative 1. So a negative x is equal to negative 1 plus 2z. But multiplying both sides by a negative, you get x is equal to 1 minus 2z. And if you write your solution as an ordered triple, you will get 1 minus 2z, negative 2z, z, which, by the way, was our original intended solution. 1 minus 2z, negative 2z, and z. So this is a cool way to kind of create your own system that has an infinite number of solutions. There you go. That's how you create systems. It's good for practicing, and if you're ever out without a book and you need to practice before an exam or something like that, that's exactly how you could do it.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.